Yeah. So thanks for the nice introduction. So my name is Zhang, and I'm a postdoc in CISPA, Sarda University. So today I'm going to present our work titled Walk2Friends, Inferring Social Links from Mobility Profiles. This is joint work with Michael Bacchus, Matthias Humbert, and Yun Pang. So the development of ICT technologies has digitalized people's mobility traces for the first time in the human history. So nowadays, if you're using your smartphone, there are multiple ways for your mobility traces to be digitalized. For instance, almost all the smart apps are actually ask you to grant them the access for a location. Or if you're using social networks, nowadays almost all social networks enable this function, saying that you can share a location in social networks, which is also called check-in. So in a way, it's good because this large amount of mobility data can help us to build appealing applications. For example, location recommendation. Let's say, find me the nearest Japanese restaurant and that's the best. So you can use this to build this kind of location recommender. Or in a bigger goal, you can do something called smart city. So I think a couple of weeks ago, there's a EU project started called Making City Works. And among this, I mean, in this whole project, smart city is a big thing there. So on the other hand, location privacy become a issue. So it turns out that people's mobility traces is considered one of the hardest or one of the most privacy sensitive information. So back in 2013, researchers from MIT already discovered that if you're only using 4 spatial temporal points, it is enough to uniquely identify a person with a 95% chance. So back in 2012, actually a paper published on CCS, they discovered that actually mobility traces can be effectively de-anonymized, use, for example, social networks as a side channel. So the third thing that is quite sensitive about mobility data is so-called you are where you go. So it turns out that the place that you go can actually leak a lot of your personal information, such as your demographics. For example, if you always go to a German restaurant, then the chance that you are German is higher than other countries. On the other hand, so actually where you go can also leak who you know. So that's the focus of this paper. So social relation. So why social relation privacy matters? So it turns out that social relations can be sensitive in many contexts. For example, office romance, in some case. Or empirically, researchers back in 2011 discovered that Facebook users in New York, the proportion of them to hide their social networks increased from 17% to 56%. Another thing is back in 2013, there's a report from Washington Post, I think, is saying that NSA has a thing called a co-traveler program. What they do is that they collect a large amount of mobility trace and try to infer their person of interest, who they know each other or not. And that's the focus of this paper. So let me state it relatively more formally. So we want to predict whether 2 users are friends based on the locations they have visited. So what's the first solution? So the most obvious solution is if we want to infer 2 user friendship based on the places they have been to, the first thing you could do is focus on the common locations they have been to. Okay, for example, all the data mining approaches take this way. In that domain, they develop many very nice features for the machine learning model. For example, location entropy, basically the thing to characterize the popularity of a certain location. And the assumption there is that if 2 users visit some unpopular location, then the chance that you know each other is much higher. However, there's a problem with this approach. That is, it can predict users, 2 user friendship only if they share the same location information and the same place. So in this case, it can predict them, their social relations, but not theirs, because these 2 users do not share any common location. And based on our data set, the empirical study, we discovered that at least 50% of the pair of users actually share no common locations. So which means this approach cannot work on them. On the other hand, you could do something more general. So you somehow can organize each user's mobility traces into a somehow mobility profile. For example, how many kilometers you travel every day, or how often you go to a certain place. And you can define, I don't know, 100, 200 different dimensions, and each user will have a same dimension mobility features. And then you can use it to do some comparison. And the central assumption is that friends are more similar than strangers in terms of mobility profiles. But however, so this somehow falls into the domain of feature engineering. So I'm pretty sure many of people here have use the machine learning in their projects. So if you start a project with machine learning, the hardest part is not actually what kind of model you choose, but actually it's feature engineering. So you need to spend a lot of time to find out what's the meaningful features that you use for a machine learning model. And in the end, it's very time consuming. So as a PhD student, you may end up doing a lot of work for 3 months, and in the end, you realize that your features still make no sense. And this happened every single time. So can we do it better? So it turns out that the recent advancement of representation learning provides us with an alternative approach. And a more familiar term with representation learning is also called deep learning. So in this setting, so you are not actually using deep neural networks or neural networks to do any classification, but actually you use deep neural networks, organize your raw data into somehow features. So basically you are not learning the prediction, but you are learning the features. Okay, so they normally follow a general object. So in many cases, people also refer this as the unsupervised feature learning. And the recent advancement on social network setting is called the graph representation learning, also called graph embedding. So what they do is they define a general object, that is, you let each user the features to preserve your neighborhood. In this sense, if two users share a similar neighborhood, then the chance that you know each other, then these features can actually reflect your social status or your position in social networks to a large extent. And inspired by this, we see whether we can adapt this approach into the mobility setting. It's called mobility feature learning. So our assumption is that a user's mobility neighbors can summarize his mobility profiles to a large extent. So based on this assumption, so clearly we have two things to do. First, what do we mean by mobility features? Second, how do we learn the mobility features? And the third thing is we need, in the end, make the prediction. So let's start with the first step, so mobility neighbors. So a user mobility neighbors, well, a obvious solution is usually include all locations you visited, as well as all the users that visit these locations, and all the locations that this user visits. So basically what I'm describing here is more like a breadth first search, right? So, but however, there's one problem, actually two problems with this approach. One is most of the real world networks actually exhibit this small world phenomena, which means if you do, let's say, 4 steps away, you probably include, I don't know, 10,000 different user and location in your mobility profile. This is highly inefficient. Second, it does not considering the, let's say, the visiting frequency. Let's say I only been to this hotel once, but I went to my office every day. But in this approach, you treat these two locations the same. Okay, this is also cannot actually reflect users' mobility profile well. So instead, what we do is we do random walk sampling. So what I mean by that is we simply first organize user and location into a bipartite graph. Here, the edge, secret edge means that reflects the frequency, that secret edge more frequently you visit the location. So how we do the random walk, so we start from each user, we do a sampling, to this location, then to her, this location, this him, and this location, and her, and this location, so on. Okay, and you apply it to all the users. So you end up with a bunch of location profile, a bunch of, actually this is a truncated random walk trace. And then once you have this, you define mobility neighbors. For example, if I want to define mobility neighbors of her, so I simply choose 2 users and locations that are precedent and after her in all the mobility traces. So in this case, all the user and locations in this blue box are actually her neighbors. After you have these neighbors, now we show how to learn the features. So basically, it's so-called feature learning, or in our case, actually, we want to learn a function theta that map all the users into a continuous vector space with a dimension d. Okay, so the general principle of our learning is actually you use each node to predict its neighbors. So what I mean by that, so let's give this tiny example. So that let's say we have this tiny mobility trace, truncated random walk trace. And let's say for him, what I mean by each user to predict his mobility neighbors. So we simply do a maximum molecular estimation so in this case, he has 3 neighbors, 1 location and 2 users. So we simply put this here. And you also do it for all the users as well as all the locations. Okay, in the end, this is simply a maximum molecular estimation. And then what do I mean by this conditional probability P? Here, so simply you can use a common practice in deep learning called softmax. you can model that. So that's the whole thing of how we learn the features. But why this works, that's why this can actually reflect user mobility neighbors. So let's say this, how this works. Okay, so so these two users, you see this guy with the blue jacket and the lady with this pink shirt. So they have somehow have quite similar mobility neighbors. In that case, in the formula sense, the features are more or less similar. In this sense, if you two users share similar mobility features, your feature mobility neighbors, then your mobility feature will be similar based on this function. Okay. After you learn all the mobility features of each user, because now each feature actually become your mobility feature actually become a vector with a dimension d, and then how we do prediction. So what we do is simply the following. So for two users mobility features, we simply compare their vector similarity. So in this sense, we got let's say in this case we got these values. And how do you make the prediction? So you simply train the threshold. Let's suppose that you want to predict all the users whose similarity is about 0.2 as friends. So you predict them all as friends. And if you keep on training your threshold, you get different predictions. Okay? And this similarity value here is so-called cosine similarity. And the whole thing is unsupervised. What I mean by that is if you recall all our process, we do not take into account any existing social networks. So instead, we just simply all use the mobility features. And since now each user will have a mobility feature, or mobility profile we learned, so actually this approach can predict any people's friendship, any two users' friendship. Okay? So let's see some evaluation. So we rely on Instagram to collect our data set. So Instagram nowadays is the second largest social networks. And one nice thing about Instagram is people there, or users there, are really likely to share their location compared to other social network platforms like Twitter. And we focus on 3 major cities, including New York, Los Angeles, and London. And another nice thing about Instagram is its location information or location profile used to link with Foursquare, which means we are not only knowing that you are at what place, we are not only knowing that your geo coordinates, but also actually we know the fine-grained information about what this place is. For example, this room A2 Dallas Sheraton Hotel. If someone establishes location in Foursquare, we actually know you are actually exactly at this location. Okay? And for the social relations, we simply consider two users who follow each other as friends. And we further do some data pre-processing. So we only focus on users who share at least 20 check-ins. And in the end, we end up in 3 cities about 5 million check-ins in total. Okay, so for your information, so if you're interested in this data set, just send me an email. Okay, so once we have this data set and our whole thing is unsupervised, so the evaluation metric we use is simply the ROC curve. So here you can see that in all the 3 cities, the performance is pretty good. Okay, so if you somehow want to achieve a 0.8 true positive rate, which actually is recall, your false positive rate is about 0.3. Okay, and the whole thing, since it's unsupervised, so this result is quite good. Another thing is, if you recall that when we compare two users' mobility profiles, what we use is cosine similarity. But of course, in the Euclidean space, you have a bunch of different similarity or distance metrics. So we also compare all these different distance metrics. It turns out cosine similarity, correlation coefficient, which is very similar to cosine similarity, as well as Bree-Curtis distance, performed best, and outperform other metrics like Euclidean distance. And interestingly, so cosine similarity, correlation, and Bree-Curtis, these all 3 metrics are somehow bounded, which means in our setting at least, if you want to measure the vector distance, you should go to this kind of metrics. Okay, so we further implement 14 baselines among all the literatures that who tackle the same problem. It turns out that this red bar is our result, and our result outperforms them significantly. Especially for LA, our performance gain is up to 20%. As I said, so our prediction can actually apply to any pair of users' friendship. However, many literature or many solutions in the literature only focus on users who have common locations. So we simply can also compare with that settings. So we only compare a subset of users who share at least one common location. And even in that case, our result is still much better than all the baseline models. This demonstrates that our current method is somehow is a state of art. So yes, another thing, let's evaluate the robustness of our prediction. So as I said, so we have pre-processing with our data set. We only focus on users with at least 20 check-ins. How about we lower the threshold a bit? We start with 5. So how about we all focus on users who share at least 5 check-ins? This makes the number of users much larger. So here the figure shows that if you increase this threshold value, the performance goes linear as expected, because more location you share, better we can profile mobility. However, even when user only share 5 check-ins, our AUC is still around 0.74 in New York and Los Angeles, which means this method actually is quite robust. Another thing is we can predict any pair of user friendship, okay, no matter whether they have common location or not. And this figure shows us that even 2 users share no common location, we can still make the AUC about 0.7 for New York and Los Angeles. So why is this the case? Because this somehow sounds like magic. The 2 users have never go to a common location, we can still make them prediction quite good. Well, if you recall the random walk traces, somehow if 2 users, even though they share no common locations, but they may go to a different location, and this location was visited by another same user. So this sense, the random walk trace somehow establish some implicit links between the users. This is why we can still achieve pretty good performance when users share no common location. So another thing is, by now our prediction is based on our data set saying that we know the exact locations that you are, right? So the POI, in the case, point of interest. But in many data sets, you actually only have the user as well as the GR coordinates, which is the latitude and longitude. We also test that in that case, let's say our data set only have latitude and longitude, and we simply cut the area by small box. And in the lowest granularity, we still achieve pretty good performance. So in the sense that, in the lowest value, in the lowest or finest granularity, our result is approaching our original result. And if you keep on enlarge or make it coarse grain, the performance drops. But interestingly, so the drop in LA is not as much as New York and London. Well, the reason is simply because compared to London and New York, LA cover a much larger area, and the city is less denser compared to the other two. That's why if you only focus on bounding box, you larger one, you still didn't lose that much mobility profile. So after the attack, let's talk about defense. So we focus on 3 defense mechanisms. The first one is hiding. So what we do is simply hide a certain proportion of locations from each user. And then for replacement, so we use approach that was proposed, inspired by approach that proposed 2013 in NDSS on this random walk thing. But this random walk is different from our previous random walk. So what we do is from each user, you start a random walk for a certain step. And then if the random walk end up at a certain location, then you simply replace your current check-in location with the location they end up. The third thing is so-called generalization. So this is inspired or similar method as the paper by EPFL on 2015 NDSS. What we do is we generalize, instead of telling me that you are exactly at this certain location, I'm telling you that I generalize the location to higher GR coordinates as well as your category. What this means is that if you're at MoMA, so Museum of Modern Art in New York, so after this generalization approach, you end up like being at an art place at this GR coordinates. Okay? But however, we further give a little bit more power to the attacker because we first recover the exact location first. Because if you tell me that you are at this location, what's the possibility that, what's the chance that you are either at a MoMA or a thing called the Towson Alternates Frog? Okay, so I don't know for you guys, but at least for me, it's more likely that I'm at MoMA because the formal place to me is more popular or famous than the other one. So we give the attacker more power with some simple side channel information, and then we first recover your generalization first. Then we can evaluate how the attacker performed in this situation. So here we show some, next is the utility metric. So our utility metric is the following. So we first summarize each user's check-in distribution among all the locations he visits. Then we simply compare the check-in distribution in the original dataset as well as the obfuscated dataset. And then we measure this distance or distribution difference with Johnson-Shannon divergence. And in the end, we average over all the users. Okay, the higher the value, more similar, the obfuscated data set is close to the original one, so higher the utility. So here the defense evaluation. So we randomly delete from 10% and up to 90% check-ins to see the performance. As you can see here, so the y-axis here is the AUC, and if you of course, if you delete more or replace more locations, the AUC drops, which means the privacy got better. However, the replacement performance is better than deletion. Okay? Why is this the case? Because if you only randomly delete something, you somehow your mobility profile is still there. You just make it less information, but the mobility profile is there. But if you use replacement, you somehow confuse the feature learning model, because the place that you never been to is the place. Well, the place you never been to now become part of your mobility profile. On the other hand, even though the replacement give better privacy, however, deletion following the same reason, so deletion actually keeps better utility, because as I said again, so all your information are still there. It's just the number of distribution are more or less there, but the number of just the quantity drops. Okay, the third thing is the generalization. So as you see that if we generalize in the finest grained level, the performance didn't drop that much. This is the result for New York. On the other hand, so if you keep on generalize it, the performance drops. However, if you in our setting, so the chorus or the largest granularity generalization, the utility drop a lot. However, another interesting value here is 52%. If you recall that I said that we first do the location recovery in the generalization, and with our very simple method, we are able to actually recover 52% of the generalization result. And this is only in New York. Actually, in LA, I think we achieve like 70%. Okay, so and if you put all the three defense mechanisms together in one figure, you can see a hiding and replacement somehow achieve a similar performance. It seems that hiding preserve better utility, but the replacement give us better privacy. Okay, on the other hand, both mechanisms outperform generalization much more. Okay, so in conclusion, so we propose a new social relation inference attack with mobility profiles. So our novelty of our framework is we are not using any feature engineering, but we actually learn each user mobility profile. And then our attack is unsupervised, and it can actually predict any two-paired user friendship. And we also propose 3 defense mechanisms, and the results show that the replacement and hiding outperform generalization. And if you're interested in the data set or the program, the code, just please send me email. Okay, so that's the end of my talk. Thank you for your attention. Questions will be appreciated. Thanks.
Tianhao Wang from Purdue University. So very nice talk and very nice work. And the question is, have you ever considered other defense techniques, for example, differential privacy and the location privacy?
Yeah, for that we haven't considered that, but it could be interesting way to go. But for that we didn't do this. Thanks.
Hi, my name is Murtuza Jadliwala from Wichita State. Couple of questions, very good work.
Yeah.
So the first question is, you consider locations and the number of location check-ins for inferring social relationships, right? Can you use additional information like contextual information like time, and will that improve your model? And the second question is, I'm kind of failing to see what's the practical usefulness of this research, in the sense, do we expect the adversary to have access to mobility profiles from companies like Foursquare in order to carry out this attack? So how will the adversary get hold or make any use of this research?
Okay, so first question, so other information than the current information we use. So we try to actually use time, but the time, what we do is simply organize the user and the location into bipartite graph. But here on the right side, or on this side, is not the location anymore, it's just spatial temporal point. And we try these kind of models, but actually it doesn't work. Because time is a tricky thing to consider. Because you somehow, in the end, you always need to involve some certain threshold. Let's see, how do you consider time? Let's see, its granularity is 1 hour or 2 hours, 3 hours. It's a bit tricky. We're actually working on that. But by now, we didn't figure out a way to make the performance better because this, as I said, the previous approach I used actually didn't gain us any benefits, even a little bit worse than the current one. And for the practical use, I mean, one thing you could do is, for example, I mean, all the many telecommunication companies now they release their data set, and for your geo coordinates, actually you can use this to infer the friendship that the two people share. But we don't expect any the attacker know detailed information about, let's say, how to say that. So for example, the Foursquare information, we don't assume that. But if he considers those things together, then you will somehow have a, in that sense, the attacker has too much information. The result may be better, but we haven't considered in that direction.
Okay, thank you.
Bimal Vishwanath, University of Chicago. So I have a very basic question about, could you go to your ROC curve slide?
Yeah.
So when I look at this curve, I'm struggling to understand why this is a good result, because I'm not sure what is a good false positive rate that you want to tolerate. So if you're looking at a large data set, I'm assuming anything even more than 1% false positive is probably bad. And if you look at the Y at that point, it is not a very impressive result. So could you?
So this is a good question because, well, at least in all the machine learning things, so normally when we show some result, you always say, okay, let's say focus on precision, we focus on recall, so our recall is good, precision is bad, something like that. But the nice thing about the ROC curve, because the AUC value resulted under that, there somehow exists a conventional standard to interpret this. Okay, so they say that if your AUC is about 0.9, this is an excellent prediction. If about 0.8, it's already good. So that's the only thing I can say. Because, yeah, this you never know. If you focus on precision, maybe the different result will be different. But of course, that one, you will always involve a certain threshold.
Yeah, I think you understand my concern. I think ROC is more explanatory than the AOC point. So if you look at this, it gives a wrong picture, I feel, when you just look at the AUC data point that you have in the later plots. This also makes me wonder if this is the best compared to even prior work, how would their ROC curves look like? So
the ROC curve, we have tried that, but we didn't show it.
Okay.
But
it would look worse, I would believe, right?
Yeah, because here you have see the AUC value here.
Okay.
Like that. Many of them are even close to random, 0.5.
Okay.
So yeah.
Okay, thanks.
Thanks for the very nice talk. I'm Kimia Tajik from Oregon State University. My question is, have you ever considered or looked at getting users' input, for instance, using like reinforcement learning methods to have like user input to balance your privacy and the utility of the network, like seeing what the users really want and having like a more flexible framework?
This is an interesting question, but what's your object of your reinforcement learning in this
Pardon
sense?
me?
So you say that maybe you can use reinforcement learning to make it better, right? So
Right.
which means your reinforcement, what's your object? So what's your cost function?
So
of
like
that?
generally I was thinking that maybe like a good approach would be like providing a little bit of more formalism to define your utility. So using that, because I think your model is very flexible in terms of defining what your utility is. So I wanted to ask you, like, do you think like there would be future research in defining the utility and then defining your cost function for the reinforcement learning or other like feedback learning methods to provide more flexibility for the users?
Yeah, I think there will be, but but not the current moment. But yeah, might be interesting direction to go. But yeah, but now we haven't considered about that.
Okay, thank you.
So it's interesting work. For your user profile, when you build the user profile, it may change over time. Did you consider the how you can update the user profile over time?
Yeah, this somehow look like an online learning setting. So basically, you have new data coming in, you can make it better. We haven't tried that direction yet, but actually, if for in terms of running the model, it's fine because you simply can keep on retraining. I mean, you rerun a random walk, then you train the model. But I'm not sure the result will be better. But at this, I'm not sure. But yeah, might be an interesting way to go. So which means, but in general, if you share more locations, probably the profile is more precise. Probably the result will be better. Probably.
Sure. Yeah, if you go by city, I think maybe the model should be static in that case. So the profile should be static. Yeah.
Maybe. But yeah.
Okay. Thank you.
Hello, I'm Huaxin from Intel Lab, and my question is, how do you define the relationship in your ground truth and the data set?
All right.
It's just because they are friends?
They follow each other, and we consider them friends. But besides that, we also do some filtering. For example, we filter out the top 10% of the users with most number of followers to try to evade all the celebrities. We also delete all the bots, which has no follower or 10 followers.
Yeah,
but for that, we can never be sure about that.
Okay, yeah. So you mean so maybe they can follow to each other on the social network, but in the real world they cannot. Maybe they don't even know each other.
That might be true, but not necessarily. At least according to my own personal Twitter profile.
Okay.
The people who follow each other with me, I know them.
Yeah. I also have a question about the data. So when you crawl your data, so can you see like one person's order relationship of them?
What?
For example, if you want to crawl to crawl all the friends of a user, but maybe the API will not allow you to collect all the friends of the user.
Well, yeah, if you go to Instagram API now, yes, no, you cannot collect anymore. But luckily, we collect this 2016 March, I guess. That time is before 2 months before Instagram closes API. So if you want to do the implementation still, you simply run the page in the API, and you get all the friends.
Okay, thank you very much.